Hey there, in this video I want to talk about solving differential equations, and we're going to begin doing that using something called Euler's Method, which is a pretty straightforward method. It's not too hard to even just come up with it on your own. I guess Euler beat us all to it, so his name's attached to it instead of any of our names. But the basic idea here is, let's say we have a first order ordinary differential equation. So that's going to be something that looks like dx dt. We're going to put that on the left-hand side of the equation, and on the right-hand side of the equation, we're going to have some combination of x's and t's. So generically, we just write that as some function of x and t. And we could always write a first-order equation in that sort of form. And now the basic idea here with Euler's method is we are going to pick some kind of starting point. So that would be something like an x initial, and we would set that at a corresponding t initial. These are called our initial conditions. And then once we have those set, we're going to do an iterative method to find with increasing time to find what x is at those times. So if we're going to take a step size h here, so that represents some tiny time step, x at t plus that tiny time step is going to be equal to x at a previous time step plus that small time step times the derivative of x. And these are really just the first couple terms in the Taylor expansion. And by definition from up here, the derivative of x is that function of x and t. So if we put that all together, once we render it, starting here with this initial condition, we just keep evaluating new values of x using the old value plus a tiny step times the slope. And that's Euler's method. So let's try it out with some code. Now what we're going to find out here is that it works okay. And if h is really, really tiny, it works actually pretty well. But it requires a lot of steps if you want a lot of accuracy. So anyway, let's come up with something simple. Let's do f of x and t like a trig function. Let's do, say, cosine. And we know that if we solve that differential equation, we should get sine. And we're going to pick some step size. Let's start with 0.01. And now what I'm going to do is, for a bunch of time values, evaluate x at each of those time values. So we'll call this array time values. And I'm going to build it with an a range. And the reason for that is because I have a step size h. And so to make sure that the steps in here match what I just said h was, let's go, well, pi would just be half of it. So we'll go 0 to 2 pi, and we'll take steps of size h. And then corresponding to that, we are going to build some x values. I'm going to make this as a list, and then we're going to fill it in using append. And then if we need to, we can convert it to an array when we're done. So this is all going to be built around a big for loop. So for every time in time values. So to get started, we have to have our initial condition. I cannot spell. Okay, so our initial condition is, so that's our x at time 0. And then we're going to keep updating that as we go. And so the update step is going to look like this. We're going to take x and set it equal to its old value plus h times the function we defined above, and that's going to give us a new value for x. And I want to stash these values somewhere, so I'm going to put them into that empty list by appending them. And I want to make sure I do this step first to make sure my initial condition ends up inside the array I'm building. If I appended afterwards, I mean, that would be okay, but I'd actually be out of sync because my first time value is 0, and I want to make sure my first x value is 0, so I have to append it first. This does mean we kind of waste the last step, but, you know, oh well, we're doing so many of them, losing one doesn't really matter. So now let's make a plot of what we get here. So we're going to plot our t values and our x values. And I already have matplotlib imported here. And let's make them discrete dots, which we have a lot of steps here, so they're all going to just blend together. But we're going to see what happens as we turn down the step size in just a moment. And then for reference, let's plot an axis here, because this thing should be symmetric around the x-axis. We'll make it black colored. And then we'll show it. Let's see if this works for us. Yeah, okay, so that looks like a sine to me. And then, you know, we can add a little bit of extra code here to check our answer. Since we know the answer is supposed to be sine, what we could do here is just explicitly plot a sine function for every t value. And we'll just let that be the default blue line. That means our dots will change to orange. Okay, and it looks like they're on top of each other. And that's good, because our step size is plenty small enough here. Now let's try changing our step size down to 0.1. We're going to take bigger steps. And now we see we start to diverge here. So this is kind of the weakness of Euler's method, is it can sort of go out of sync. And if we made this really big, then of course we're going to have an absolutely terrible fit to our function. So let's go put that back at, say, 0.1 was okay. Kind of nice, intermediate, close enough sort of value. Let's look at what happens if we change our initial condition here. So like, what if I made my initial condition 1? What does that do? Well, that means that I'm starting at the value 1, and then I'm continuing to plot. That means, of course, down here, this line is not accurate anymore. So you can see we still get the same kind of shape, but with a different initial condition, you start at a different spot. And so in this case, it gives us from 1 to 2 down to 0. So you might reason if we change this to 2, we'd move farther up, and so on. Okay, so that's what's kind of like the purpose of the initial conditions, is where are you starting for a given time. We could also do something like, let's start at a different time value. Let's start at 1 instead of starting at t equals 0 and see what that does. And upon doing so, you can see here when our time is 0, or when our time is 1, first thing in our t array, we started at 1, and then we continued graphing from there. And you could play around with these and get different sort of functions. So when t is 1, we're at 0. But we still get the same shape, right? And because the differential equation is telling you what the shape is going to be. Okay, so that's it for this method. You can try it out in the example below, and then we're going to look at some more higher order methods coming up.